This building is moving right now, not collapsing, not failing, moving. Even if the sky is clear, even if there's no wind you can feel, even if everything looks perfectly solid, if you were standing at the top of this skyscraper, the floor beneath your feet would be slowly shifting sideways, by centimeters, sometimes more. And here's the part most people never expect. If this building stopped moving completely, it would actually be more dangerous. Today, you're going to understand why the tallest buildings on Earth are designed to bend, sway, and absorb motion, and why rigidity, the thing we instinctively associate with strength, is one of the fastest ways to make a structure fail. By the end of this video, you'll never look at a skyscraper the same way again. And if you enjoy discovering the hidden limits of engineering, the quiet rules that keep massive structures standing, subscribe to the channel. This is exactly what we explore here. Let's start with a belief almost everyone has. We grow up thinking that strong structures don't move, that the safest bridge is the stiffest one, that a solid building should feel like a rock. That idea feels intuitive, but engineering doesn't care about intuition. It cares about how forces flow. Every structure on Earth is constantly under attack. Not dramatic attacks, not disasters. Small, continuous forces. Wind pushes against buildings every second of every day. Temperature changes make materials expand and contract. Traffic, elevators, machinery, and even footsteps send vibrations through the structure. The ground itself is never completely still. None of these forces are impressive on their own. But structures don't fail because of one big force. They fail because of millions of small ones that never stop. Now, imagine a skyscraper that is perfectly rigid. When wind hits it, the building refuses to move. So where does the energy go? It doesn't disappear. It travels. The force moves through beams, columns, joints, and connections, concentrating stress in specific locations. Over time, that stress causes microscopic damage, tiny cracks, material fatigue, weak points that grow silently. This is how structures fail without warning. Early skyscrapers taught engineers this lesson the hard way. When cities first began building upward, the goal was simple: make buildings as stiff as possible. Steel frames were designed to resist motion at all costs. On paper, they looked incredibly strong. In reality, they were storing energy. Wind loads didn't get absorbed. They got redirected downward. Stress piled up in columns and joints. Over years, buildings aged faster than expected. Not from storms, from normal days. Engineers realized the problem wasn't that buildings were too weak. They were too rigid. So the philosophy changed. Instead of asking, how do we stop this building from moving? Engineers started asking, how should this building move? That single shift changed everything. Modern skyscrapers are not designed to resist motion. They are designed to manage it. When wind pushes against a tall building, the structure bends slightly. Not enough to see from the street. Not enough to feel unsafe, but enough to absorb energy. That bending spreads forces across the entire structure, reducing stress at any single point. The building survives by yielding. This idea exists everywhere in nature. Trees don't fight the wind. They bend. If a tree were perfectly rigid, it would snap during the first major storm. Flexibility is not weakness. It's survival. But allowing buildings to move introduces a new problem. Humans hate motion. You don't need danger to feel uncomfortable. You only need acceleration. Even tiny movements, ones that are completely safe structurally, can cause dizziness, nausea, or panic. So engineers had to solve a strange challenge. How do you let a building move without people feeling it? The answer is one of the most elegant solutions in structural engineering. Inside many of the world's tallest buildings sits something massive, sometimes hundreds of tons, sometimes more. It doesn't hold the building up. It doesn't support floors or walls. It moves. This is called a tuned mass damper. When the building sways in one direction, this massive object moves in the opposite direction. The two motions cancel each other out. The building still moves, but far less. To the structure, the force is reduced. To the people inside, the motion becomes almost invisible. Some dampers are giant pendulums hanging near the top of the building. Others are enormous concrete blocks mounted on rails. Some use water tanks that slosh back and forth, perfectly timed with the building's movement. Different designs, same principle. Motion is not eliminated, it's controlled. This is the same idea used in noise-canceling headphones. You don't block sound. You introduce an opposite signal that neutralizes it. Skyscrapers do the same thing, but with wind and gravity. And wind is only part of the story. Earthquakes push this philosophy even further. During an earthquake, the ground itself moves violently. If a building is rigidly connected to the ground, that motion transfers directly into the structure. The result is extreme internal stress. Modern skyscrapers often avoid this by doing something counterintuitive. They partially disconnect from the ground. Base isolation systems use massive bearings and sliding interfaces that allow the building to move independently of the shaking earth. Instead of fighting the earthquake, the building rides it. The ground moves. The building moves less. Once again, survival comes from controlled motion, not resistance. This leads to one of the most important ideas in modern engineering. Strength is not about resisting force, it's about shaping how force flows. A rigid structure stores energy. A flexible structure dissipates it. Stored energy always finds a way out. Dissipated energy fades harmlessly away. That's why engineers obsess over how structures behave over time, not just how they behave at maximum load. A building that survives a storm but slowly accumulates damage is not safe. A building that gently moves every day without concentrating stress can last for generations. This is why modern skyscrapers are designed to sway within carefully calculated limits. Too much movement feels unsafe to people. Too little movement damages the structure. There is a narrow, intentional balance, and it's constantly monitored. Sensors inside tall buildings measure acceleration, displacement, and vibration. Engineers track how the structure responds to wind, temperature, and occupancy. The building is alive with data, not because it's fragile, but because it's valuable. Now here's the part that surprises most people. You don't need a storm for a skyscraper to move. On a clear day with no noticeable wind at street level, the top of a tall building can still sway. Why? Because wind speed increases with height. At the ground, air is slowed by buildings, trees, and terrain. Higher up, wind flows freely, so while you feel nothing below, the upper floors are experiencing constant pressure. That pressure is enough to cause motion, and that motion is intentional. If a skyscraper felt perfectly still, engineers would be concerned. Stillness means energy is being trapped. Movement means the system is working. This philosophy doesn't just apply to skyscrapers. Bridges flex under load. Ships bend with waves. Airplane wings deform constantly during flight. If aircraft wings were rigid, they would tear themselves apart. Instead, they bend upward, absorbing lift forces and turbulence. Once you see this pattern, you see it everywhere. The most reliable structures are the ones that know how to move. This changes how we define safety. Safety is not about eliminating motion. It's about making motion predictable. A building that moves exactly as expected is safer than one that doesn't move at all. That's why engineers test buildings in wind tunnels. They simulate storms, gusts, and turbulence, not to see if the building breaks, but to see how it moves. They measure frequency, amplitude, and damping. They're not asking, will this collapse? They're asking, does this behave the way we designed it to? Because when a structure behaves predictably, it can be trusted, and trust is what keeps cities standing. So the next time you look up at a skyscraper disappearing into the clouds, remember this. That building is not defying nature by standing tall. It is cooperating with it. It bends, it sways, it yields. Not because it's weak, but because that's the only way something that large can survive in a world that never stops pushing. The tallest buildings on Earth don't stand still to stay safe. They stay safe because they know exactly how to move.